Hello there, and welcome to Just About Earth, where curiosity gets cozy and science drifts quietly between the folds of wonder and rest. Tonight we're going to travel very, very far, not in space, but in time. Because long before cats curled beside fireplaces or birds greeted the morning with song, long before legs or jaws or thoughts, there were animals, the very first ones. Small, strange, often overlooked, but they were there. And that's our gentle question tonight. Who were they? The first animals? Not just life. Life is ancient, but animals. Creatures that moved, sensed, fed, multiplied. Creatures that were not plants or fungi or mats of algae clinging to stone. When did they appear? How did they begin? And how do we even know when the trail they left behind is softer than breath? Let me ask you, wherever you're listening from, have you ever thought about the very first creature that felt something? The first ripple of sensation? It's easy to forget that every squirrel, whale, dragonfly and human is part of a lineage that goes back hundreds of millions of years. But someone had to be first, and if you're finding this thought quietly fascinating, or just a comforting thing to drift off to at the end of your day, I'd be grateful if you'd give this video a like, maybe subscribe, or share it with someone else who enjoys a bedtime stroll through deep time. Now, I do hope this won't be so interesting it keeps you wide-eyed, but if it does, well, you'll at least learn something about your ancient relatives before you drift into dreams, so settle in. Let your thoughts slow, let your breath soften, and let's begin. Because to tell the story of the first animals, we have to rewind time, not a few decades or centuries, not even millions of years. We're going back over 600 million years to a time when Earth was cold, almost entirely frozen, and the surface was a canvas of ice and silence. And yet, somehow, somewhere, something began to stir. Not a dinosaur, not even a fish, but something alive, something animal. And that, dear traveller, is the beginning of our story. It began, as these things often do, with something small, not with a grand announcement or a thunderous revelation, but with a puzzle, a pattern in the rocks, a strange ripple in stone. In a windswept corner of South Australia, not far from the cliffs of the Flinders Ranges, a geologist named Reg Sprigg was looking for uranium in 1946. He didn't find any, but he did find fossils, lots of them. Unfamiliar, ghostly impressions in the sandstone, like the outlines of sleeping creatures that had long since vanished. They looked like leaves, or jellyfish, or something entirely unknown, and they were old. Far older than anyone expected animals to be. At the time, the scientific consensus was that complex life had exploded into being during the Cambrian period, about 541 million years ago. Before that, it was thought, there had been nothing but single-celled algae and bacteria. But these rocks were older than the Cambrian, much older, by at least 20 million years. Some eventually turned out to be 100 million years older. This shouldn't have been possible, and yet, here they were, soft, enigmatic impressions in ancient stone. Fossils of creatures that had no bones, no shells, and no known place in the tree of life. Sprigg didn't know what to call them. No one did. But decades later, they'd come to be known as the Ediacaran biota, named after the Ediacara Hills where they were first discovered, and they weren't just local curiosities. Similar fossils began to turn up elsewhere. Newfoundland, Namibia, Russia, England, always in rocks of similar age, always strange, always just slightly out of reach, like memories from a dream. These discoveries sparked a question that has rippled through science ever since. Were these the first animals? To answer that, we have to understand what an animal actually is. It sounds obvious, surely we know, but in biology, words often stretch beyond their everyday meaning. Animals are not just things with fur or feathers or bones. At their simplest, they are multicellular organisms that eat. They don't make their own food like plants. They don't absorb it like fungi. They ingest it. They move, or at least they have the capacity to. They reproduce. They have cells without rigid walls. They often have specialized tissues and nervous systems, though not always. In essence, they are creatures made of many cooperating parts, alive with motion and hunger and sensation. And for most of Earth's history, they didn't exist. Let that settle for a moment. For billions of years, life was small, microbial, invisible to the eye. The world was shaped by bacteria. Cyanobacteria that filled the atmosphere with oxygen, archaea that lived in boiling vents, single-celled eukaryotes that drifted like specks in the sea. Complex cells with nuclei and organelles emerged somewhere around 2 billion years ago. But still, for ages upon ages, nothing squirmed or crawled or saw. The Earth was not silent. Microbes are industrious things, but it was still in a deeper way. No animals, no minds, no motion but the tides. Then, something changed. It didn't happen in a single moment. There was no trumpet blast, no flick of a divine switch. But over millions of years, cells began to cooperate more closely. They clumped, they organized, they communicated. And eventually they differentiated, some cells becoming digestive, others sensory, others muscular. The Great Leap was not from fish to frog or ape to human, but from one cell to many, working as one. This was the true evolution, the birth of bodies. And those first bodies? They are hidden deep in time, glimpsed only through the rarest of fossils, molecular whispers in ancient rocks, and the branching codes of DNA that still echo with ancestral instructions. Today, a scientist might not start their search for the first animals with a rock hammer, but with a microscope, or a centrifuge, or a computer modelling the mutations of proteins across eons. Because the story of the first animals isn't just carved in stone, it's written in the genes of sponges and jellyfish and worms, in the chemistry of ancient ocean mud, in the shadows of long-vanished biomes. Take chonoflagellates, for example, tiny, single-celled organisms that live in water, wafting their collar-like whips to capture food. On their own, they seem unremarkable, but genetically they are our closest known relatives outside the animal kingdom. Some can even form colonies, hinting at the ancient steps toward multicellularity. Their genomes contain many of the same genes used by animals to communicate between cells, to stick together, to develop structure. These are not animals, but they are animalish. Perhaps the last link in the chain before animals truly began. And when animals did begin, when true, multicellular, ingesting, moving organisms first wriggled into existence, it's likely that no one noticed. There were no eyes to see it, no minds to ponder it, but the oceans noticed. Quietly, irrevocably, the balance shifted. The world grew a new kind of complexity. Fossils tell us part of this story, but so do molecules. By comparing the genes of living animals, scientists have pieced together evolutionary family trees that stretch back before fossils can follow. This method, called molecular clock analysis, uses the rate at which DNA mutates to estimate how long ago two species diverged from a common ancestor. It's not perfect, like estimating a tree's age by measuring its height and guessing the rate of growth, but it gives us a ballpark, and those ballparks suggest that animals may have originated over 800 million years ago, long before the Ediacaran fossils first appeared. But if they were there, where were they? That's where things get slippery. Early animals were soft-bodied, squishy, not the kind of thing that fossilizes well, especially in a world where sediment was different. Microbial mats covered the seafloor, and predators, if they existed at all, were more like vacuums than jaws. So for millions of years, animals may have existed quietly, without a trace, living out their soft lives in the shadows of stone. Then something stirred again. Around 575 million years ago, we begin to see the strange quilted forms of the Ediacaran biota. Dickinsonia with its ribbed oval body, like a mattress left in the rain. Sprigina, segmented like a flattened worm, yet with no mouth or eyes. Frond like Charnia, anchored to the sea floor, swaying gently in ancient currents. Some of these may have been animals, others, well, no one is entirely sure. They might have been something else altogether, a failed experiment in multicellularity, an evolutionary dead end, a different kingdom of life, now vanished. Paleontologists still argue, and gently so, because mystery is part of the charm. But even if the Ediacarans were not true animals, they were something astonishing. Large, complex, macroscopic life. And they set the stage for what would come next. For in the layers just above them, in rocks a little younger, a new kind of fossil begins to appear, one with teeth. Not metaphorical ones, actual biting, grasping, burrowing traits. Here begins the arms race of evolution. The Cambrian explosion is only a few million years away now, and with it the rise of creatures that swim, hunt, and leave behind trails in the mud. But before that burst of exuberance there were these pioneers, the maybe animals, the almost animals, the quiet stirrings before the storm, and to understand how we found them, how we even know they existed, we must follow not just one scientist but generations. Paleobiologists, geochemists, field geologists and fossil hunters, trudging through the desert, through Arctic cliffs and forested coasts, looking for signs in rock that life had shifted. One such trail comes from steranes, molecular fossils, traces of cholesterol-like compounds found in sedimentary rocks. Some steranes are thought to come specifically from animals, and their presence in rocks over 635 million years old has tantalized researchers with the idea that animals might predate their own fossils by tens of millions of years. Then there's oxygen, the invisible actor on which everything depends. For complex multicellular life to thrive, a certain threshold of oxygen is required in the oceans, and around the time the first animal-like fossils appear, we begin to see chemical signatures in rocks that suggest oxygen levels were rising. Slowly, unevenly, but enough. Enough to breathe, enough to move. And so the story begins to converge. A rise in oxygen, a blossoming of genetic complexity, the presence of chonoflagellate-like ancestors, the stirrings of soft bodies in sediment, the first fronds, the first patterns, the first whispers that the animal kingdom had awoken. It didn't happen all at once. It wasn't a parade, but step by step, layer by layer, rock by ancient rock, we begin to see the outline. And even if some of the earliest creatures defy classification, even if some were more closely related to fungi or to no living thing at all, they represent the threshold, the moment when life began to sculpt itself into something new, something that would one day walk and sing and build ships to the stars. And so we owe a quiet gratitude to these strange ancestors, not because they looked like us, but because they made us possible. The trail is faint, the clues are rare, but they're enough. Just enough to whisper, animals were here. And they began not with a roar, but with a ripple. To imagine the first animals, we must first imagine their world. And that world was not ours. It was older, colder, stranger. The continents, if they existed at all in familiar shapes, were not where we left them. They huddled near the equator, battered and reformed by a million slow collisions. Most of the land was barren. No trees, no grasses, not even moss, just rock. Bare, ancient rock, weathered by winds that had never touched a flower. The only life was in the sea, and the sea, the sea, was everything. The ocean was where it all began, a vast planetary womb. It covered more of Earth's surface than it does now, stretching wide and deep, blanketing the planet in saline stillness. There were no fish, no sharks, no coral reefs. But the water teemed with microbial life, invisible and endless. Bacteria swirled in the sunlight, harvesting energy from the sun, from sulfur, from iron. Filaments of cyanobacteria formed mats across shallow sea floors, pulsing with photosynthesis and patience. Above, the sky was dimmer. The sun, younger by billions of years, shone a little less fiercely. The atmosphere was thick with carbon dioxide and methane, then thinned, then thickened again. There were no birds to mark the wind, no insects to stir the air. The Earth breathed in geological time, and time was long. This was the Ediacaran period, named after those curious fossils we spoke of before. It followed one of the most dramatic chapters in Earth's history, a global glaciation so intense it's sometimes called Snowball Earth. Around 720 million years ago, glaciers spread from pole to equator, covering much of the planet in ice. Entire oceans may have frozen over, a gleaming, blinding mirror wrapped around the globe, and yet life endured. In the thin cracks where sunlight could still reach, near hydrothermal vents, beneath the ice, in dark, pressurized worlds warmed by the planet's internal heat, microbes survived. And when the ice receded, slowly, over millions of years, it left behind a changed world. A world washed in nutrients, a world stirred by oxygen, a world ready for complexity. It's easy to overlook what a miracle this was. Ice doesn't just chill, it stifles, it locks away energy. But when that ice melted, it flooded the oceans with phosphates and minerals, fueling blooms of photosynthetic life. Cyanobacteria roared back, algae flourished, and the atmosphere, long starved of breathable air, began to rise in oxygen once more. This mattered, because complex life needs oxygen, not just a trace, but a steady supply. The machinery of multicellular bodies, of movement and nerves and digestion, is costly. It burns energy, and that energy comes from oxygen. So as levels crept upward, slowly and unevenly, they crossed a threshold, and in the shallows, among the microbial mats, something new began to form. Picture it. The seafloor is a patchwork of slimy carpets, green and purple films of bacteria, layered in time. The water above is murky, thick with plankton. Light filters through in dappled shafts bending across ripples in the sand. And nestled there, in the quiet spaces between, a creature moves. It does not look like anything alive today. It has no eyes, no limbs, no bones. It may be little more than a flattened disc, or a soft tube, or a branching frond anchored to the sediment. But it moves, or rather it flows. Perhaps it undulates to feed. Perhaps it absorbs nutrients through its skin. Perhaps it drifts, rudderless, on chemical tides. It is not the first life, but it is one of the first animals. Some of these early creatures may have been filter feeders, grazing on microbial mats. Others might have absorbed dissolved nutrients from the water. Still others, we suspect, began to specialize, some into mouth parts, others into muscle. Even here, in their simplicity, we begin to see the outlines of strategies still used today. The ambush, the crawl, the dig, the drift. One such creature might have been Kimberella, a soft-bodied organism with a shell-like shape and a distinct front and back. Fossil evidence suggests it could move, and perhaps even graze, scraping bacteria from surfaces with a primitive rasping structure. Some scientists think Kimberella might have been a very early relative of mollusks, placing it firmly within the animal kingdom. Others urge caution. The fossil is ambiguous. The past rarely hands us its secrets so plainly. Still, the implications are profound. This was a creature with direction, with behaviour, with choice. Nearby, other forms appear. Dickinsonia, with its segmented oval body, lies flat against the sediment like a soft-ribbed doormat. It has no known limbs, mouth or gut, but some fossilised impressions show possible signs of movement or growth. Chemical analysis of its preserved tissues suggests the presence of cholesterol, a molecule found almost exclusively in animals. That alone has ignited debates. Was Dickinsonia one of us? or just close. These were not monsters. They were not hunters or swimmers, but they were alive. They were organised. They were new. As more and more of these impressions came to light, in Australia, in Russia's White Sea, in Canada and Namibia, a picture began to form. This was not a one-off. This was a fauna. A whole community of life sprawling across the seabed, fronds like Charniodiscus, swaying in the current, anchored by holdfasts. Quilt-patterned forms like Fractophusus, fractal in structure, as if geometry itself had dreamed of life. Tubes, discs, blimps, spirals, some large enough to cover a dinner plate, others delicate as lace. Most had no heads, no mouths, no symmetry we'd recognise. But they lived, they grew, they died. This was not a blank canvas, it was a garden. And yet, despite their beauty, these creatures remain elusive. Most left no descendants. Their anatomies are alien, their affinities uncertain. Some may not have been animals at all, but a separate experiment in multicellular life. Perhaps a now extinct kingdom, branching off early, before our own animal lineage took shape. Still, among them, perhaps hidden in plain sight, were the ancestors of sponges, of worms, of jellyfish, of us. Let's take a step closer. Imagine one of those shallow Ediacaran seas. The water is warm, nutrient-rich, thick with life. Microbial mats coat the seabed like velvet. Above, colonies of algae drift and bloom, and in the mud below, an ecosystem hums. Sponges filtering particles, worms tunnelling, soft-bodied creatures slowly creeping from place to place. No eyes, no sound, but still interaction, feeding, competition, perhaps even the first flickers of predation. For the first time in Earth's long history, life is beginning to sense and respond. The dance of stimulus and response, of detection and decision begins here, and with that comes something new. Not just life reacting chemically, but processing. Some creatures begin to develop nerve nets, primitive, decentralized networks of neurons. These are not brains, not yet. But they are something remarkable, a way to integrate information, to touch, to taste, to twitch in response. Alongside them come muscles, contractile tissues, ways to move not just with cilia or flagella, but with purpose. The Ediacaran Ocean is beginning to wriggle, and perhaps most importantly there is symmetry, bilateral symmetry, a front and a back, a left and right. This too is a quiet revolution. With a front comes direction. With a direction comes the need for coordination, for decisions, for movement, for hunting. It is from this bilateral blueprint that most modern animals descend. Insects, mammals, mollusks, birds, all trace their roots to these early trailblazers. And while the Ediacaran garden was largely sessile, anchored, rooted, drifting, it planted the seeds for what would come next, a world of motion. But that world was not yet here. The Ediacaran was a time of gentle experimentation, of soft steps and slow changes. No claws, no shells, no chase. That would change in the next act, the Cambrian. But before that curtain rose, Earth offered a moment of calm, of quiet complexity, of life in slow bloom, and it's worth pausing to reflect on just how radical this world was. For 3 billion years life had been microscopic. Now, at last, the macroscopic world was awakening. Size had advantages. It allowed organisms to interact in new ways, to engineer their surroundings, to shape their ecosystems. It allowed specialization, internal cavities, organ systems, circulation, digestion, movement. And yet the world remained silent in our sense of the word. No song, no cry, no eyes watching the stars. But beneath the waves, evolution was laying the foundations, not just for animals, but for future minds. You might think, standing on a modern beach watching waves roll across sand, that you're seeing something timeless. But the waves are old. The animals, the crabs, the birds, the people with their beach towels, they are new. Their ancestors trace back through fish, through worms, through blobs and fronds and crawling mats, all the way to the Ediacaran, all the way to the moment when Earth first learned to feel. If the Ediacaran world was a garden, it was a quiet one, a strange, slow, swaying dreamscape at the bottom of a warm, shallow seas. Life had blossomed in soft forms, with no bones or shells or teeth. It drifted. It clung. It grazed gently. For millions of years this was enough. But then something shifted, and it did not shift quietly. The next chapter in Earth's story is one of the most dramatic, the most sudden and the most debated in all of biology, the Cambrian explosion. It sounds like a bang, like fireworks or thunder, but it wasn't a single moment. It was an acceleration, a blossoming, a rush of biological innovation that unfolded over roughly 20 to 25 million years, beginning about 541 million years ago. In geological terms, that's the blink of an eye. And in that blink, the animal kingdom as we know it appeared. Not just one or two new forms, but dozens. Entire body plans, the fundamental blueprints for building an animal, emerged during this time. Arthropods with jointed limbs, mollusks with muscular feet and protective shells, worms that burrowed and tunneled, sponges filtering water with elaborate chambers, cnidarians with stinging tentacles, and the earliest chordates, our own ancestors defined by a simple stiff rod down the back. It was the debut of complex movement, of predation, of armour and attack and evasion. Eyes evolved, real eyes, with lenses and retinas and resolution. Jaws of a sort, claws, burrowing limbs, tentacles, and behind all of it, a flurry of new behaviours. Before the Cambrian, life mostly lay still. Afterward, it chased. So what triggered it? The question has captivated scientists for centuries, because while it's clear that something remarkable happened, the why remains an exquisite puzzle. Was it a change in the environment? A burst of oxygen? A genetic breakthrough? A cascade of evolutionary dominoes? Or was it all of these things, layered, timed, and tangled together? Let's begin with oxygen. Oxygen, though it floats invisibly around us now, was once a trace gas. Before 2.5 billion years ago, it was almost non-existent in Earth's atmosphere. Then came the Great Oxidation Event, thanks to cyanobacteria and their tireless photosynthesis. But even after oxygen began to accumulate, it took billions of years to reach the levels needed to support large active animals. By the late Ediacaran and into the Cambrian, geochemical evidence shows that oxygen levels rose sharply, possibly reaching thresholds that allowed for energetically expensive lifestyles, like active swimming, burrowing and hunting. Muscles need oxygen. Nervous systems need oxygen. And once oxygen became widely available, it's possible that evolution had the fuel it needed to run. But fuel isn't enough. You also need instructions. And here, genetics enters the scene. Sometime before the Cambrian, perhaps during the quiet ages of the Ediacaran, a genetic innovation occurred that changed everything. The emergence of developmental toolkits. These are the genes that control how an embryo becomes an organism, where the head goes, where the limbs grow, how tissues differentiate. Among the most famous of these are the Hox genes. Hox genes are astonishing. They're like molecular architects laying out the body plan of an animal from front to back. And what's most surprising is that these genes are deeply conserved. You, a human being, have Hox genes. So does a fly. So does a worm. So probably did the earliest bilaterally symmetrical animals. Once these toolkits were in place, evolution could begin rearranging them. Not building from scratch, but tinkering. Adding segments, shifting limbs, duplicating structures. It's like giving nature a new set of Lego bricks. The parts were there. Now they could be assembled in a dazzling variety of ways, and so they were. Fossil sites from the Cambrian are some of the most spectacular in paleontology. Chief among them is the Burgess Shale, a limestone deposit high in the Canadian Rockies, discovered in 1909 by Charles Doolittle Woolcott. Within these rocks are the preserved bodies of Cambrian creatures, many soft-bodied, detailed to an almost miraculous degree. Their anatomy is visible in full: legs, eyes, guts, even traces of behaviour. Here we meet Opabinia, with 5 eyes and a long flexible snout ending in a claw. Anomalocaris, a predator with grasping appendages and circular toothy jaws, possibly the apex hunter of its time. Hallucigenia, a spiny worm that looked like something from a dream, or perhaps a mild hallucination, hence the name. And Picaia, a simple chordate that may represent one of the earliest vertebrate ancestors. These animals weren't just odd, they were new kinds of odd. Nothing like them exists today, and some represent entire branches of life that flourished for a while, then disappeared. But others, like early arthropods, sponges and chordates, would go on to dominate Earth for the next 500 million years. How did they get here? How did such an explosion of form happen in such a short time? Another clue lies in the sediment itself. Before the Cambrian, most seafloors were covered in stable microbial mats, layered films of bacteria that formed a kind of living pavement. But during the Cambrian, something began to disturb those mats. Creatures started burrowing, digging into the sediment, churning it like living ploughs. This is the agronomic revolution. A shift from static, mat-covered seafloors to dynamic, mixed-up sediments. It changed everything. Burrowing opened new habitats, allowed for more oxygen penetration, and created a feedback loop of ecological complexity. The sea bottom became an ecosystem, not just a surface, and with that came competition. Before, creatures could feed passively, sucking nutrients from mats or drifting plankton. But now, with mobile animals wriggling through the mud, food became contested. Creatures had to move, to seek, to escape. And in that crucible, natural selection intensified. Here's a quiet irony. It may have been predators, the chasers and the biters, that fueled the explosion of life. Predation creates pressure. It drives prey to adapt, to hide, to harden, to run. And those adaptations create new niches, new ways to live and survive. Armour begets jaws. Jaws begets speed. Speed begets complexity. And so evolution began to accelerate, folding on itself, branching, spiralling, racing into the future. Even the fossil record changed. With the rise of hard parts, shells, spines, exoskeletons, more animals began to preserve. The stone caught their outlines, their struggles, their innovations. Finally, they left footprints in time. But perhaps the most important change wasn't physical at all. It was ecological. The Cambrian explosion wasn't just about new bodies, it was about new interactions. For the first time, animals began to build ecosystems, interconnected webs of life with producers, consumers, detritivores, predators. The sea became a theatre of relationships, and that shift, from solitary existence to intricate community, is what truly defines the Cambrian. From it, all later complexity would grow. Still, it's tempting to think of this as inevitable, as though animals were always destined to rise, to build, to flourish. But nothing in nature is guaranteed. The Cambrian explosion could have failed. A change in chemistry, a shift in climate, a delayed oxygenation. It might never have happened. We might still be a planet of slime. But it did happen, and it changed the course of Earth forever. We might imagine in our modern world of buzzing cities and blinking screens that complexity is a natural trajectory, that things, once begun, always build upward. But in Earth's history, nothing is guaranteed. Complexity is precious, but it is also fragile. It flickers, it hesitates, it collapses, and during the Cambrian, it very nearly didn't rise at all. Because even now, even with fossils in hand and genomes decoded, the Cambrian explosion is still an enigma. One of those rare moments in science where the evidence is vivid, but the cause remains soft-edged. We can trace the outlines, but not the spark. Some theories suggest that it wasn't a trigger, but a threshold that was crossed. That for millions of years, life had been quietly building up the necessary components: genes, cell types, oxygen, food chains, and then, one day, or rather one age, they all came together, like a chemical reaction that finally had all the ingredients, like lightning in a cloud already humming with charge. Others point to the co-evolution of life and environment. Perhaps early animals didn't just respond to changes, they caused them. Burrowing disturbed sediments, filtering cleared water, excreting waste changed the chemistry of the ocean. In other words, animals were not just passengers of the Cambrian, they were the drivers. There's even a theory involving calcium. As more calcium washed into the oceans, it may have become toxic to soft-bodied creatures unless they developed a way to store or manage it. And what better way than to build shells? Armour, bones, teeth. Biological innovation born of chemical stress. Suddenly, defence and structure became a bonus, not a burden. Or consider the role of light. Before the Cambrian, the oceans were murkier. Plankton and microbial mats clouded the shallows. But as ecosystems shifted and new organisms filtered the water, visibility increased. And with clear water came new possibilities. Photosynthesis deeper down, vision at longer range. Eyes may have evolved in part because there was finally something to see. That simple shift from blindness to vision reshaped the animal world. The evolution of eyes was not a trivial step. It allowed for new forms of behaviour: pursuit, navigation, precision. Trilobites developed compound eyes with hundreds of tiny lenses, a marvel of engineering that rivals the best optical designs today. And with eyes came the birth of landscapes. For the first time, animals experienced not just proximity but perspective. They could sense distance, shape, motion. The ocean floor became not just a surface but a terrain. But even as complexity bloomed, extinction loomed nearby. Many of the creatures we find in Cambrian rocks are not ancestors. They're cousins, side branches, experimental forms. The tree of life, even here, was pruned as often as it grew. The Cambrian was not a straight line. It was a bush, sprawling and tangled, many shoots curling into dead ends. And this makes sense. Evolution doesn't plan. It does not seek perfection. It wanders, tries, discards, repeats. What we see in the fossil record are not the best solutions, but the ones that survived long enough to fossilize. Beneath them lie countless others, lost, erased, folded back into the earth. This is why the incompleteness of the record matters. The Cambrian explosion may not have been a true explosion. It may be that earlier animal life simply wasn't preserved. Too soft, too rare, too scattered. Some scientists argue that the explosion is an illusion, an artifact of fossilization. The animals might have evolved gradually, we just didn't find them until they left harder parts behind. But even if the explosion was partly a trick of the stone, the result was still real, the aftermath was still profound. Animals were here, and they were doing things never done before. One of the more curious signs of the Cambrian's transformational nature is found not in skeletons, but in trace fossils, the marks left behind by living creatures. Burrows, tracks, feeding grooves. These tell us how animals behaved, not just how they looked. And during the Cambrian, these traces become deeper, more complex, more varied. Suddenly, animals weren't just on the seafloor. They were in it, moving through it, building structures, changing its chemistry. The Earth's surface was no longer a passive stage. It became a dynamic, living interface, where life shaped geology and geology shaped life. And speaking of trace fossils, there is one found in Namibia, known simply as Treptichnus pedum. It looks like a series of overlapping burrows, looping and branching in a curious pattern, and it marks, by international geological convention, the base of the Cambrian period. It's not a bone or a shell, it's a behaviour, a moment when life got cleverer with movement. The creature that made it? We don't know. It didn't leave its body behind. But its trail was enough to rewrite history. Still, the Cambrian world remained alien. These were not ecosystems we'd recognise. There were no plants, no land animals, no predators with backbones or lungs, no insects in the air, no roots in the soil. Just a teeming marine biosphere, entirely underwater, humming with new activity. And yet, it worked. Photosynthetic plankton fed filter feeders. Filter feeders fed grazers. Grazers fed hunters. Detritivores cleaned up the rest. For the first time, Earth supported complex food webs, capable of sustaining ecosystems for millions of years. And all of it arose from small beginnings, from soft bodies that grew hungry, from silent, shivering cells that found new ways to cooperate. And so we return to the original question: what caused the Cambrian explosion? And the answer, it seems, is everything. A rise in oxygen, a genetic toolkit, the coevolution of predators and prey, changing ocean chemistry, ecological engineering, a shifting climate, light, sight, teeth, shells, muscles, burrows, competition, chaos. No single match lit the fire, but many sparks fell and the sea caught flame, and the consequences, they echo still, because every animal alive today, every whale, ant, bird and human, descends from the experiments of the Cambrian. Your limbs, your mouth, your spine, your eyes. They are Cambrian legacies, ancient blueprints passed down through hundreds of millions of years, modified and refined, but never truly abandoned. And within you, too, are echoes of things lost. The discarded branches, the failed designs, the forgotten cousins, the trilobites that scuttled across ancient seabeds, the velvet worms with their sticky limbs, the armoured oddities whose names we still debate. You are a living museum, a collection of successes. But the Cambrian was filled with stories we'll never know, lives unrecorded, shapes unpreserved, whispered once and then gone. Perhaps that's why the Cambrian explosion feels so haunting. It is not just the birth of modern animal life, it is also the ghost forest of everything that might have been. And yet, here you are, listening, breathing, moving, a direct descendant of that unfathomable bloom. And somewhere in the core of your cells your body still remembers the instructions that built the first eyes, the genes that once laid out a simple, bilateral shape, the muscles that first moved to chase. They're still here, still humming, still evolving. And so, as we step forward into the next chapter, the chain reactions, the collapses, the recoveries, it's worth pausing here, just for a moment, to honour the fire lit beneath the waves and the quiet, soft-bodied ancestors who first dared to move toward the light. If the Cambrian explosion was a spark, what followed was wildfire, slow burning by human standards, but in geological time, a blaze of breathtaking speed. Animals had emerged not just in form, but in action. They burrowed, they swam, they hunted, they built. And the world they entered, the one that had cradled soft-bodied fronds and mats of microbial stillness, began to change in response, drastically, irrevocably. The seas grew restless. Imagine, if you will, the shallow margins of a Cambrian sea. Not the deep abyss, but the near shore zones, where light still reached the seabed and nutrients ran thick. Here, life had once been tranquil. Microbial mats coated the sediment in dense, rubbery films, holding it in place like glue. These mats had dominated Earth's oceans for billions of years, creating stable, oxygen-poor habitats with little disruption. In many ways, they were the seafloor's skin. But now those mats were being torn apart. New creatures had arrived, animals capable of burrowing, chewing, churning the sediment with soft, squirming bodies. These weren't predators in the traditional sense. They weren't chasing anything. But they were disturbers, architects of change. With every inch they dug, they mixed oxygen deeper into the sediment. They broke the microbial crust. They stirred up nutrients, and toxins. In doing so, they opened space for other creatures and closed it off for those that had depended on stillness. It was the beginning of bioturbation, a fancy term for the biological remixing of sediment. And though it sounds mild, it was revolutionary. These first burrowers transformed the seafloor from a passive backdrop into an interactive surface, layered with microhabitats, gradients and chemical shifts. It was as though someone had lifted the lid on a quiet aquarium and swirled the water with a spoon. This had cascading effects. Oxygen could now penetrate deeper, fueling more metabolism. Sulfides and methane trapped in the anoxic layers below were released. Entire microbial ecosystems collapsed or relocated. Filter feeders, once confined to mats and crevices, could now thrive in newly oxygenated zones. And with this mixing came mobility. Creatures began to migrate vertically as well as horizontally, feeding in the mud, hiding, laying eggs. The seafloor became a three-dimensional world. But with new space came new competition. The Cambrian didn't just give us new body shapes, it gave us new ecological roles, and those roles created pressure. One of the earliest arms races unfolded in slow motion beneath the sea. As soft-bodied grazers spread, predators began to adapt. The fossils of the time tell the tale. Early arthropods developed grasping limbs, circular jaws evolved, hardened plates appeared, then spines, then armour. The first defensive morphologies, features built not to feed but to survive. Predation, once rare, became common. No longer could a creature simply lie in wait, siphoning nutrients from its surroundings. Now to live meant to respond, to move, to protect, to strategize in biological terms. Some responded with speed. They developed paddle-like limbs, streamlined bodies, segmentation for controlled flexing. Others relied on deception, camouflage, burrowing, nocturnal habits. Still others grew shells, spines and toxins. Every adaptation in the hunter spurred a counter-adaptation in the prey, and vice versa. This loop, this spiralling dance of escalation, is known in biology as evolutionary arms racing. It doesn't require malice, just pressure, persistence, and time. And it left marks not only on bodies, but on the chemistry of the oceans themselves. As more creatures built shells, from calcium carbonate or silica, the demand for those minerals increased. Ocean chemistry shifted to accommodate it. Vast swathes of the seafloor became covered in shell fragments, layering into chalk and limestone that still form cliffs and mountains today. In time, whole ecosystems began to rely on hard parts, coral reefs, exoskeletons, toothy grazers, and the consequences rippled outward. More skeletons meant more dead matter sinking to the seafloor. This organic rain-fed scavengers created thick layers of carbon-rich sludge and set the stage for long-term carbon burial. Over millions of years, this burial helped draw carbon dioxide out of the atmosphere, altering climate. It was one of Earth's earliest large-scale carbon sinks tied directly to the rise of animals, and where carbon goes, climate follows. There is evidence to suggest that as animal life intensified in the oceans, Earth's climate cooled slightly. Subtle, perhaps, but meaningful. These weren't ice ages yet, not like the brutal Snowball Earth episodes of the Precambrian, but gentle glacial murmurs that hinted at a new dynamic. That life, once passive in the face of geology, could now shape the planet in return. This feedback loop between life and Earth, between biology and geology, is one of the most powerful ideas in modern science. It's sometimes called Earth system science, and the Cambrian represents one of its first major inflections. Life wasn't just reacting to the world, it was engineering it, and as the planet shifted, so too did the food web. Before the Cambrian, most energy had trickled slowly through mats and microbes. Afterward, it flowed through networks of consumers, filter feeders, grazers, predators, scavengers. Energy moved not just from sun to algae to bacteria, but across trophic levels, from prey to predator. from host to parasite, from death to decay to rebirth. For the first time in Earth's history, food chains became food webs, complex interconnected systems where each creature's role influenced countless others. And these webs were not stable. When one species vanished or adapted, others had to follow suit. Coevolution became a way of life. Creatures didn't just evolve in isolation anymore. They evolved with each other, tangled together in a quiet war of necessity. This had its costs. In the aftermath of the Cambrian explosion, Earth experienced waves of extinction, local and global events that wiped out entire lineages. Some were likely caused by competition, others by shifting chemistry, some by climate, and some perhaps by sheer bad luck. Because even with all this innovation, the Cambrian world was still experimental. Many of its creatures were evolutionary one-offs, brief, brilliant branches that flourished for a time, then disappeared. They left no descendants, no modern analogues, just impressions in stone, fossils with no storybook endings. And in a way, that makes their existence more poignant. We often think of evolution as a ladder, a march toward complexity. But it's more like a field, sprawling, uneven, full of false starts and forgotten turns. For every successful lineage, 1,000 vanished. For every vertebrate, a dozen vanished designs. The winners of history are not necessarily the most elegant, just the most adaptable or the most fortunate. Among those that did survive, however, were the building blocks of modern ecosystems. Sponges still filtering water today, unchanged in their quiet grace. Worms forever digging. Arthropods, with their jointed limbs and hard shells, exploding into a million shapes and strategies. And the early chordates, us in our simplest form. Little swimmers with notochords, precursors to spines, rudimentary tails, muscle bands, slits for breathing. They didn't roar, they didn't rule, but they endured. And in time, they would give rise to fish, to amphibians, to dinosaurs and mammals, to humans sitting in quiet rooms, wondering how it all began. But back then, they were just one thread in the tapestry. And the tapestry was vast. In the next part, we'll follow that thread forward. We'll watch what happened next, not just to the animals that survived, but to the planet that carried them, the next extinctions, the first recoveries, and how the world reshaped itself around its newest residents. But before we go there, let's pause here, because for a moment, just a moment, the seas were alive in a way they had never been before. Creatures stirred in the mud, shapes flashed in the light, shells clicked in the current, and for the first time, life wasn't just surviving, it was thriving. But for all its beauty, the Cambrian world was a house of cards, complex, layered, dazzling, and inherently unstable. Because complexity, for all its evolutionary charm, comes with a price. It needs balance. It needs time. It needs just enough disturbance to innovate, but not so much as to collapse. And after the Cambrian's great flowering, Earth began to tip once more toward imbalance. The seas had become full of forms, of functions, of newly invented lives. But with invention came vulnerability. Species were now bound together in tight webs, each thread depending on countless others. And when just a few threads were snipped, the effects could cascade. Like dominoes, one fall could trigger another. A scavenger loses its prey, a grazer loses its algae, a predator grows too good at hunting, a reef collapses, and ocean chemistry drifts just slightly too far in one direction. The first major extinction events after the Cambrian aren't as famous as the Big Five that would come later, the end Permian, the end Cretaceous, but they were real, and they were sobering. Sometime in the late Cambrian, around 485 million years ago, many of the flourishing animal groups began to disappear. Trilobites, which had diversified into hundreds of species, declined. Brachiopods faltered. Whole reef-building communities blinked out. The causes are still debated. Perhaps a cooling climate, or a drop in sea level, or a disruption in the carbon cycle. Perhaps, as always, it was several things at once. There's a lesson there. What we do know is this. Earth was still learning how to host complex life. It was not yet a stable landlord. Oxygen levels fluctuated, nutrient flows shifted, currents reversed, mountains rose and fell, volcanoes burped carbon into the sky, continents wandered, reshaping shorelines, pinching off shallow seas, opening new ones, and through it all the animals endured, changed, adapted, or didn't. It's strange to think that the very forces that give rise to life can also undo it. That the planet doesn't particularly care about complexity. It offers the ingredients, but it also stirs the pot. Take the carbon cycle, for example. During the Cambrian, as more animals grew shells, more carbon was buried in the form of calcium carbonate. This should, in theory, have drawn down atmospheric carbon dioxide, cooling the climate. And in part it did. But then, tectonic activity, uplift and erosion, exposed ancient rocks, releasing carbon back. Volcanoes added their own emissions. The balance wobbled. And ecosystems felt every wobble. Even small changes in carbon dioxide can shift ocean acidity, making it harder for marine animals to build shells. Coral-like organisms struggle. Filter feeders collapse. Predators lose their prey. This wasn't just theory. It was happening in cycles, over and over in Earth's early oceans, and with every collapse came an opportunity, a reset. The extinction of one lineage opened space for another. Empty niches invited innovation. After the early extinctions, new types of arthropods appeared. Early jawless fish began to stir in the depths. Primitive vertebrates, slow-moving, armour-plated. Soon they would dominate. But in the Cambrian and shortly after, they were minor players. Most of the sea still belonged to invertebrates, creatures without backbones. Trilobites, in particular, diversified into thousands of species scuttling across every corner of the seafloor. They were the beetles of the Paleozoic, adaptable and ubiquitous. And yet, they too would falter. In time. Because extinction, like evolution, is a constant presence in life's story. It's not a failure. It's part of the pattern. Even as new forms emerged, others disappeared. The Cambrian had its share of strange, singular creatures, species so unique that when they vanished, no echo remained. Creatures like Wiwaxia, covered in spines and scales, part mollusk, part mystery. Or Nectocaris, an early soft-bodied swimmer with traits of both arthropods and cephalopods. Or Vetulicolians, segmented filter feeders with no clear lineage. Some paleontologists argue they were early chordates. Others suggest something stranger, a now extinct phylum. These were not ancestors, they were experiments. And the Earth, ever the curious tinkerer, let them try, and then, gently, quietly, closed the door on them. We often imagine extinction as a drama. Comets, volcanoes, floods, and sometimes it is. But more often, it's a drift. A species dwindles, birth rates fall, food sources vanish, competitors grow more efficient, and over millennia the lights go out. But light elsewhere grows brighter, because for every lineage that failed to adapt, another rose to fill the space. This is the paradox of extinction. It is both loss and opportunity. Sorrow and seed. And in the aftermath of the Cambrian, we see this pattern unfold in full. The early Ordovician period, which followed the Cambrian, became a time of renewal. Diversity rebounded. New groups of animals emerged. Coral-like organisms began to form rudimentary reef systems. The ocean stabilized, at least briefly, and new ecological layers appeared, not just on the seafloor but in the water column above. Life began to claim vertical space, rising into new depths. This was a quiet revolution of its own, because once creatures began to move upward, to swim, to hover, to hunt in open water, entirely new ecosystems emerged. Planktonic feeders, active swimmers, agile predators with body plans built for efficiency, jet propulsion, Fin strokes, undulating ribbons of muscle. Here, fish began their slow ascent. Still simple, still jawless, but unmistakably vertebrate. Their emergence set the stage for the next great leap. For now, though, they shared the sea with an astonishing array of shelled, spiny, leggy creatures, all navigating the lingering turbulence of a world not yet finished settling. Meanwhile, on land, silence. During and after the Cambrian, the continents remained largely barren. No trees, no insects, no birdsong or flowers or footprints. The land was a canvas still waiting for paint. Occasional microbial crusts may have carpeted the rocks. Perhaps a few early fungi or lichen-like forms crept across the soil. But for the most part, the Earth's land masses were as quiet as the moon. And yet, in the oceans, life was rewriting the rules of existence. Let's not forget how recent this all was, geologically speaking. Before the Cambrian, there had been 3 billion years of microbial life, single cells, mats, biofilms, and then, in just a few tens of millions of years, came skeletons, muscles, brains, behaviour, eyes that could see, mouths that could bite, burrows that shaped the ground. It wasn't just life evolving, it was Earth being rewritten. And in that rewriting, a curious truth emerged. The animals, so new, so fragile, were beginning to influence systems far larger than themselves. They changed not just local habitats, but global cycles. They drew carbon down, they pushed oxygen up, they stirred sediments, rerouted nutrients, altered the flow of phosphorus and sulfur. They affected weathering, changed water clarity, even impacted the reflectivity of Earth's surface by altering cloud-forming particles in the atmosphere. For the first time in Earth's history, biology had become a planetary force, and that, perhaps, is the real legacy of the Cambrian and its immediate aftermath. Not just the creatures themselves, marvellous though they were, but the shift from passive life to active geology, from soft-bodied mats to living, sensing, burrowing, reacting agents of change. Animals became agents, not passengers. They were no longer just shaped by the Earth, they were shaping it in return. And they would continue to, through every extinction, every recovery, every innovation that followed, because evolution does not slow down, it only pauses to breathe. The Cambrian explosion had ended. The initial rush of novelty had settled, but the aftershocks continued, rippling outward into every era that followed. From that point on, Earth would never again be quiet, and neither would life. It's tempting sometimes to think of the Cambrian explosion as the first great drama of life, the opening act, the curtain rise, the moment when nature stirred from sleep and began to write her story in limbs and shells. But that isn't quite true. Because before animals ever swam, before nervous systems ever blinked awake, there had been other stories. Older ones, stranger ones. Stories told not in motion, but in molecules. Not in bones, but in breath. Life on Earth is ancient. Far more ancient than any trilobite or worm. It began, so far as we can tell, almost 4 billion years ago, not long after the planet itself cooled from molten chaos. The details remain hazy, but in some warm little pond, or perhaps in a hydrothermal vent at the bottom of the sea, the first cells assembled. Not much more than bubbles of lipid and strands of RNA, but they replicated, they persisted, and that was enough. These were not animals, not even close. They were prokaryotes, simple cells with no nucleus, no organelles, no compartments, just chemical ambition. Bacteria and their cousins, the archaea, ruled this world. For over 1 billion years they were the only living things. They reshaped the oceans. They harvested energy from minerals, from light, from gases bubbling up from the deep earth. And they were, in their own way, astonishingly inventive. Some developed photosynthesis. Others evolved mechanisms to metabolize sulfur or iron. Some lived in boiling acid, others in ice. They explored every niche, every corner, quietly. Then, around 2.5 billion years ago, one group of bacteria made a radical choice. They began to release a byproduct, a gas that no life had yet used, a waste that was, for most organisms, toxic. That gas was oxygen, and its release changed the planet forever. This was the Great Oxidation Event, an atmospheric revolution that would poison many ancient microbes and open the door to everything that would come next. Because oxygen, while dangerous, is also powerful. It allows for far more efficient energy use, and once life learned to tolerate it, and later to use it, complexity began to stir. Still, complexity is patient. It waited. The next major leap came not in atmosphere but in architecture. Somewhere between 1.8 and 2 billion years ago, a new kind of cell emerged. Larger, compartmentalized, more sophisticated. These were the eukaryotes. They had nuclei, mitochondria, internal membranes. They were, in short, the kind of cells you're made of, and their rise wasn't gradual, it was explosive, at least by microbial standards. How did they arise? One idea, now widely accepted, is that eukaryotes are the result of symbiosis. That is, one cell engulfed another. But instead of digesting it, they formed a partnership. The engulfed cell became the mitochondrion, the powerhouse of modern animal and plant cells. Later, in plants, other engulfed cells would become chloroplasts, the engines of photosynthesis. This was evolution by merger, not mutation. Cooperation, not conquest. A cellular alliance that created the architecture for all future plants, animals, fungi and protists. And yet, even with these innovations, life remained microscopic. Multicellularity, cells sticking together to form a larger organism, seems simple now. But it took another billion years to emerge consistently. Why? Because it required not just physical adhesion, but coordination, communication between cells, genetic control over development, the ability to specialize, to form tissues, organs, shapes. Only when these abilities matured could life begin to sculpt itself into something larger than a cell. And when it did, sometime around 800 to 1,000 million years ago, the door to animals creaked open. We often mark the Cambrian as the moment animals arose, but it's likely that sponges, the simplest of all animals, originated long before, perhaps as far back as 700 million years ago. Genetic evidence suggests as much. They lack true tissues, have no nervous system, and filter feed by moving water through their porous bodies. But they are animals, by all biological definitions. They don't look like us, but they belong to our family. Then came other strange forms, ctenophores, comb jellies, cnidarians, jellyfish and corals, placozoans, all simple, all aquatic, all early. And even earlier, in the prelude to the Cambrian, were those elusive creatures of the Ediacaran, Dickinsonia, Charnia, Sprigina. Were they animals? Some probably were. Others, something else. Experiments that vanished without descendants. Still, their presence tells us something vital. Evolution didn't wait for the Cambrian to begin innovating. It had been trying, testing, tweaking for eons. The Cambrian explosion was not the beginning of life's creativity. It was its crescendo. And even then, it wasn't the last. Because just as the Cambrian was once thought to be the start of complex life, the Ordovician, which followed it, would become one of its richest elaborations. In the Ordovician period, beginning around 485 million years ago, marine ecosystems became truly layered and dynamic. Planktonic life exploded. Reefs began to grow, filter feeders flourished, mollusks diversified. The first true vertebrates, jawless fish with cartilaginous skeletons, spread through the seas. The first hints of eyes with lenses, notochords and gill slits became common, but even this bloom would be interrupted. Around 443 million years ago, near the end of the Ordovician, came the first great mass extinction. Ice sheets grew over Gondwana, a supercontinent near the South Pole. Sea levels dropped. Shallow marine habitats vanished. Temperatures plummeted. It is estimated that 85% of marine species died. This was Earth's first known planetary reset. The first time that complex life, having risen to flourish, was cut back by environmental catastrophe. But it wouldn't be the last. Mass extinctions would become a kind of heartbeat in Earth's story. A pulse of disruption. A brutal editor. The late Devonian, around 375 million years ago. The end Permian, 252 million years ago. Earth's most severe, wiping out over 90% of marine species. The end Triassic, 201 million years ago. And the end Cretaceous, 66 million years ago, when a rock from space ended the age of dinosaurs. Each of these events tore pages from life's book. But they also cleared the stage. They made room. In their aftermaths, life didn't just recover, it reinvented. After the Ordovician extinction, coral reefs came back stronger. After the Permian, mammals began their rise. After the Cretaceous, primates flourished. The lesson: life is not a line, it is a cycle. It surges, it crashes, it rebuilds. And with every crash, the survivors write the next chapter. Mass extinctions are often remembered for what they destroy. The trilobites that vanish, the forests that fall silent, the once bustling reefs that dissolve into rubble. But hidden within every extinction is a deeper pattern, not just of death, but of reset. These events strip away the overgrowth. They clear evolutionary monopolies. They unfreeze possibilities. And in that silence, new voices emerge. After the Ordovician extinction, marine ecosystems restructured. Bivalves spread. Brachiopods diversified again. Cephalopods, early relatives of squid and octopus, began to dominate certain niches. Jawless fish continued to drift and feed, gentle shadows in the water, until something even more radical appeared. Jaws. Somewhere in the Silurian or Devonian periods, evolution stumbled upon a new toolkit. The transformation of gill arches into biting structures. The jaw was not a single invention. It was a series of lucky mutations, reworked cartilage, and opportunistic anatomy. But once it arrived, it rewrote the rules. With jaws came chewing, gripping, seizing. Suddenly predation wasn't just suction and filtering, it was attack. It was selection pressure turned up to 11. Prey evolved faster. Armour became thicker, reflexes quicker, eyes sharper, and the first-jawed fish, the placoderms, heavy with armour, began to rule the seas. Later, sharks would rise from this lineage, then bony fish, then amphibians, then us. But the jaws were just one example of how Earth's history isn't a march. It's a cascade. Each breakthrough doesn't stand alone, it tumbles into the next. Consider the vertebral column. At first, a stiff notochord to give swimming bodies a sense of direction. Later, segmented bones, then ribs, then skulls, then limbs. Each change, modest on its own, eventually allows a body to crawl, to climb, to hold tools, to write music. These are the echoes of earlier decisions, stacked, inherited, transformed. Even extinction events follow patterns. Geologists and paleontologists have noticed cycles, rough rhythms in Earth's climatic, tectonic and orbital behaviour. These are not metronomes, but pulses. Glacial interglacial shifts, supercontinent cycles, volcanic flare-ups tied to mantle plumes, oceanic anoxia. Sometimes even galactic factors, as our solar system moves through denser parts of the Milky Way, possibly disturbing comet clouds or influencing solar radiation. Life, it turns out, has always been embedded in a cosmic context. And yet, despite all this upheaval, the thread of animals endured. The same genes that stitched together the first worms still hum inside your cells. The same chemical gradients that told a Cambrian trilobite how to form its limbs still guide your embryonic development. The language has changed, but the alphabet is ancient. Sometimes, evolutionary innovations get repurposed in surprising ways. Feathers, for instance, evolved first for insulation, not flight. Later, they became displays. Only eventually did they help wings catch air. Lungs, it's believed, may have first evolved as air sacs in fish, allowing them to gulp oxygen in shallow, murky waters. Later, those sacs became the lungs of amphibians, reptiles, birds, and mammals. Even brains, our most prized possession, evolved in steps. Not as a grand plan, but as an accumulation of nerve clusters. The first animals with neurons likely used them not to think, but to coordinate movement, to swim, to avoid danger, to feed. Consciousness, that slippery, dazzling thing we cherish so deeply, was a byproduct, a bonus feature. And so, we begin to see a pattern. Evolution is not progress. It is tinkering. It is chance, filtered by time, shaped by need. And yet, when you zoom out, the results seem almost inevitable. The rise of animals was not guaranteed. It could have faltered at any point. A delayed oxygen spike, a more severe glaciation, a collision of bad timing. But it didn't. Instead, life passed through bottlenecks, through filters of fire and ice, and emerged changed. Every extinction was followed by irradiation, every collapse by innovation. There is something almost poetic about that rhythm. Not romantic exactly. It comes at great cost, but poetic in its resilience, and it mirrors patterns found even beyond biology. The Earth itself forms and reforms. Continents collide and crumble. Oceans widen and shrink. Volcanoes bury. Water calves. Mountains rise and are worn down to dust, and the biosphere rides along. Take the cycle of supercontinents, a slow-motion ballet that has shaped the backdrop of evolution. Rodinia, Gondwana, Pangaea. As continents merge and break apart over hundreds of millions of years, they rearrange climates, coastlines, ocean currents, and ecosystems. When land masses come together, species compete. When they split, they diversify in isolation. Marsupials in Australia, lemurs in Madagascar, trilobites in separated Cambrian seas. Isolation breeds difference. Connection fuels struggle, and out of struggle comes change. This is why paleontologists don't just look at bones. They look at where the bones are found. In what rock, in what layer, in what continent once connected or now drifted away. Geography is a kind of second genome. It holds the context, the stage directions. It also reminds us that Earth has never been static. In the Cambrian, there were no trees. In the Ordovician, no vertebrates on land. In the Devonian, forests appeared, but insects had no wings. In the Carboniferous, the air was thick with oxygen and dragonflies the size of hawks. In the Permian, deserts spread. In the Triassic, the first dinosaurs emerged. In the Jurassic, the first birds. In the Cretaceous, the first flowering plants. And yet through all these chapters, animals endured, not as a single lineage, but as a diverse, ever-branching family tree. Sometimes the branches broke, sometimes they twisted together in new configurations, but the tree kept growing, and it grew from roots sunk deep in time, from microbes that built the first biofilms, from cells that learned to cooperate, from worms that dared to burrow, from mollusks that built shells, from predators with simple jaws. From quiet beginnings, the animal kingdom rose, not like an empire, but like a coral reef, slowly, incrementally, layer by layer, each step building on the last, and it's worth saying softly that we are not the goal of that process. Humans are remarkable, but we are one leaf on a vast ancient branch. The Earth has hosted far stranger, longer-lasting, more abundant creatures, bacteria, insects, fish. Our story is young, but it is connected. The same cycles that shaped trilobites shape us. The same sunlight that fed ancient algae grows our crops. The same volcanoes that buried Cambrian reefs still fume beneath our feet. We are not outside Earth's history. we are its most recent expression. And when we study the first animals, not just their forms but their contexts, we glimpse the deep patterns that govern life here. That extinction is not an end, but a pruning. That complexity is a double-edged gift, that ecosystems are fragile, beautiful interlocks, that life, even in its simplest form, shapes the world around it, and that nothing, absolutely nothing, is separate. The animal kingdom didn't arrive on Earth. It arose from it, piece by piece, breath by breath, just as we did. For hundreds of millions of years, the story of the first animals lay buried in stone, trapped in silt, pressed under oceans that no longer exist. Their bodies turned to shadow, their movements to trace fossils, their world unimaginable to the people who would one day walk the ground above them. And yet, one by one, those stories were found, because humans, fragile, upright, curious animals ourselves, have a peculiar habit. We dig, we question, we puzzle over patterns, we hold a rock in our hands and ask, what lived here? And somewhere along the way we realise that the Earth was not just dirt and stone, it was memory. The idea that life had a deep past wasn't always obvious. For much of history, fossils were misunderstood. Seashells on mountaintops were considered curiosities, or decorations from the Great Flood, or playful tricks of nature. Stone imitating life, not preserving it. But by the 17th and 18th centuries, minds began to shift. One of the earliest pioneers was Nicholas Steno, a Danish anatomist who, while dissecting the head of a shark in 1666, noticed something familiar. The shark's teeth looked exactly like the so-called tongue stones found embedded in rocks across Europe. These weren't tricks of stone, he realised. They were real teeth, fossilised remains of once-living animals. It was a small revelation, but from it a revolution would grow. Steno's principle of superposition, that deeper layers of rock are older than those above, became one of geology's foundational rules. Over time, as more layers were studied, more fossils unearthed, and more questions asked, the Earth's history began to unfold, chapter by buried chapter. But the story of the Cambrian explosion and the rise of the first animals would wait much longer to be told. Because the evidence for that moment in time, the most fragile, early, strange animals, was hard to find. They didn't leave bones, they didn't leave teeth. They left soft bodies, impressions, rare traces in rare rocks, preserved only under perfect conditions. Still, the hunt began. In the mid-19th century, a man named Adam Sedgwick, a geologist and clergyman, was mapping the rocks of Wales. He was among the first to notice a distinct layer of ancient rocks beneath those that held more familiar fossil forms. He named them after the region, Cambrian, from Cambria, the Latin name for Wales. He didn't know what he'd found, not yet. At the time, Darwin had just published his theory of evolution, and many scientists struggled with the sudden appearance of complex animal forms in Cambrian rocks. Where were the transitional fossils? Where were the ancestors? Even Darwin himself called it a serious objection to his theory. He believed the fossil record was incomplete, and he was right. But the lack of Precambrian animals gnawed at many. If life had evolved gradually, why did animals seem to arrive all at once? It would take another century before the fog began to lift. The breakthrough came high in the Canadian Rockies. In 1909, an American paleontologist named Charles Doolittle Walcott was hiking through Yoho National Park in British Columbia when he stumbled upon something extraordinary. A slab of shale filled with exquisite, detailed fossils of soft-bodied creatures, legs, eyes, even internal organs visible in stone. He had found the Burgess Shale. Walcott collected thousands of fossils over the next few years, carefully cataloguing, photographing, preserving. But in his effort to classify them within known groups, he may have missed their deeper significance. Many of these animals were entirely unfamiliar. Not just new species, but new body plans, strange blueprints that defied easy placement in the tree of life. It wasn't until the 1960s and 70s when a new generation of paleontologists, like Harry Whittington, Simon Conway Morris and Derek Briggs, re-examined the Burgess fossils that their full strangeness was appreciated. They found animals like Opabinia, with 5 eyes and a vacuum-like snout ending in a claw, Anomalocaris, a fearsome predator with swirling mouthparts, Hallucigenia, a spiny worm-like creature once drawn upside down. These were not our ancestors. They were failed experiments, branches pruned from the tree of life, but they revealed just how wildly creative evolution had been during the Cambrian, and they proved that soft-bodied animals had indeed left their mark, if only we knew where to look. The Burgess Shale became a window into a vanished world. But it wasn't the only one. Across the globe, other sites began to emerge. The Chengjiang fossil site in China, even older and richer than the Burgess. The Sirius Passet Formation in Greenland, the Emu Bay Shale in Australia. Each added new species, new insight, new texture to the story of early animal life. In Chengjiang, scientists discovered fossils of Milocunmingia, a tiny jawless fish with a notochord, possibly one of the earliest known vertebrates. In other slabs, they found creatures with compound eyes, complex guts, gill structures, and evidence of nervous systems. These were not half-formed animals. They were fully realized, built to move, sense, eat, and survive. Their presence confirmed what Darwin had suspected long ago, that the apparent suddenness of the Cambrian explosion was not a failure of evolution, but of preservation. With better fossil beds, the gaps began to close, and with each fossil, the human side of the story deepened. Consider the researchers who spent years in remote mountains, chiseling stone by hand, who slept in tents, braved cold, bore the weight of their doubts and theories. Consider the artists who reconstructed creatures from fragments using anatomy, inference, and imagination, or the geochemists who crushed ancient rocks to dust, extracting isotopic signals that whispered of vanished oceans. These are the people who reassembled the story, and sometimes they got it wrong. Hallucigenia was reconstructed upside down. Anomalocaris was once thought to be 3 separate animals. Mistakes happened, revisions followed. Science, after all, is a living process, a fossil in motion. Even today, debates continue. How exactly did nervous systems evolve? What were the first true animals? Did the Cambrian explosion begin earlier than we thought? Was it truly explosive, or just an artifact of preservation and attention? To answer these questions, scientists turned not just to rocks, but to genes. By comparing modern genomes of humans, sponges, jellyfish, worms, flies, they began to reconstruct the deep ancestry of animal life. Genes like the Hox family, which control body patterning, turned out to be ancient, present even in the simplest animals. These genes, remarkably conserved, allowed paleobiologists and molecular clock theorists to trace back the divergence of major animal groups. And what they found aligned with the fossil record. Most major animal lineages seem to have split before or during the Cambrian. Some, perhaps even earlier. The Cambrian explosion then was not a starting point. It was a turning point. A time when evolution began to sculpt with bolder tools, brighter palettes, and deeper ambitions. And behind every insight, every correction, every flash of discovery was a human story, a muddy boot, a careful brush, a whisper of wonder in the high alpine air. To study the first animals is to listen across silence, across 500 million years of buried time, across continents split and rejoined, through stone so old it crumbles at the touch. And the ones who chose to listen, really listen, became translators of Earth's memory. Some did it with hammers, splitting shale in wind-blown valleys. Others did it with microscopes, decoding the language of genes or the hidden symmetries of ancient shells. Still others stared into computer models, watching virtual oceans bloom with simulated life. Take Mary Wade, an Australian paleontologist who helped uncover the Emu Bay Shale, one of the richest Cambrian deposits in the southern hemisphere. or Jianhan, whose work at Chengjiang helped reveal not only fossils but entire ecosystems, predator-prey dynamics, plankton blooms, even evidence of parasitism and cannibalism in the deep past. Or Stephen Jay Gould, who didn't discover fossils himself, but gave them voice. In his book Wonderful Life, he took the strange beings of the Burgess Shale and turned them into philosophical guides, symbols of how chance and contingency shape evolution. He argued that if you replayed the tape of life, the outcome might look nothing like what we see today. No humans, no whales, perhaps no animals at all. It was a controversial idea, but a profound one, because it challenged the notion of inevitability. It reminded us that the rise of animals, and everything that followed, was not scripted. It was emergent, a product of luck, timing, context, and resilience. Gould helped people see fossils not just as artifacts but as voices, and his influence rippled outward into classrooms, museums, documentaries. He made ancient life feel personal, but others pushed back. Simon Conway Morris, Gould's contemporary and collaborator, took a different view. He saw not randomness, but convergence. The idea that evolution, given similar challenges, tends to arrive at similar solutions. Wings evolved in birds, bats, insects. Eyes appeared in squid, mammals, and jellyfish. Intelligence, sociality, cooperation all arose more than once. To Conway Morris, the rise of complexity was not a roll of the dice, but a directional pull. Not a goal, but a tendency. This debate, chance versus convergence, still hums at the edge of evolutionary science. And it doesn't need a winner. Both views have truth in them. Life is both unpredictable and patterned, surprising and familiar, and those who study it are drawn in by both forces. They are in the end storytellers. Some dig for a lifetime and find one perfect fossil, a trilobite so finely preserved it shows the curve of its eye lenses. Others work in genetic labs, comparing regulatory genes across species, tracing the molecular echoes of a jellyfish inside a chimpanzee. Some climb cliff faces, others crawl through archives, some teach, some paint, some build models from wire and resin. Each becomes a node in a network of discovery, linking past to present. And more than anything, they remind us that science is a human endeavour, full of missteps, revisions, long dry spells and moments of utter revelation. There's Morella, once thought to be a trilobite, later revealed as a totally separate lineage. There's Pikaia, a tiny chordate from the Burgess Shale, possibly among our earliest ancestors. There's Hyquichtsthis, with its simple skull and nerve cord, blinking out from rock in China. Each one found because someone kept looking, and sometimes it's not about the fossil itself, but about the context. A graduate student might notice an unusual layering in a quarry. A field geologist might spot a siltstone that's slightly too dark, slightly too fine. These small details lead to new sites, new excavations, a new animal that changes how we date a rock layer, a new isotopic ratio that redefines the global carbon cycle. It's detective work, collaborative, cumulative, and slow. Many Cambrian sites took decades to understand. Some are still being reanalyzed today. Fossils stored in drawers for half a century are now re-examined with CT scans, revealing structures invisible to the naked eye, neural tissues, guts, embryonic development. Technology, too, becomes a storyteller. 3D scanning, synchrotron radiation, AI-assisted classification. These tools allow us to revisit old finds and ask new questions. We can reconstruct how an animal moved, what it saw, how it breathed. We are, in a sense, building time machines, and each breakthrough, each newly uncovered creature, pulls the Cambrian just a little closer. But it's not just the scientists or the technologies that matter. It's us, the viewers, the listeners, the ones who sit beneath lamplight or curled under blankets wondering where animals came from. We too are part of this long chain, this vast lineage, and by asking questions, by seeking wonder, we continue what those early fossil hunters began. This is the quiet truth behind paleontology. You don't have to hold the rock to hold the story, because every child who sees a trilobite in a museum and asks what it was, every artist who paints a Cambrian reef, every reader who imagines hallucigenia walking in reverse, becomes part of the story of discovery. It's not just a scientific tale, it's a human one, of memory, imagination, and a yearning to know what came before. And if we follow that yearning backward far enough, past the scientists, past the fossils, past even the animals themselves, we return to something elemental, the earth, turning, quiet, waiting, a sea rich with minerals, a sun rising over empty shores, and in that sea a cell dividing, then dividing again. No one saw it, no one knew, but that division, that spark of persistence, would ripple forward for billions of years, through extinction and explosion, through trilobites and whales, through science and story, until one day it would become a question in the mind of an animal, a question whispered before sleep. Who were the first of us? And now, piece by piece, we begin to answer. If fossils are the fingerprints of ancient life, then science is the light we shine on them to make the prints visible. Without tools, without methods, we would have only broken stones and curious shapes, but with science those stones speak. They tell time, they whisper chemistry, they echo with genetics, they become more than rocks, they become memory. And to unlock that memory, we need to look deeper, past the creatures themselves, into the mechanisms that preserved them, the tools that revealed them, and the questions that shaped how we interpret them. Let's begin with something seemingly simple. Dating. It's one thing to find a fossil, it's another to know its age, to place it precisely on Earth's great calendar. For that, scientists rely on radiometric dating, a method that uses the slow, steady decay of radioactive elements into stable ones to tell time. Imagine a volcanic ash layer buried above or below a fossil. That ash contains zircon crystals, tiny geological time capsules. Inside those crystals are traces of uranium, which slowly decays into lead at a known rate. By measuring the ratio between the two, scientists can calculate exactly how long the crystal has existed. Not in vague eras or loose centuries, but in millions of years, with margins of error sometimes smaller than the lifespan of a single species. It's through this method that we've dated the Cambrian to around 541 million years ago, give or take a blink. But time is only the beginning, because knowing when something lived is different from knowing what it was, how it lived, and why it mattered. For that, we turn to paleobiology, the study of ancient life in all its dimensions. At its heart, paleobiology is about interpretation. Take a fossil worm. It may look like a simple tube, but with the right tools, scanning electron microscopes, synchrotron imaging, chemical staining, we can reveal fine structures, bristles, gut tracts, even nerve pathways. These details tell us how the worm moved, what it ate, whether it burrowed or swam or anchored itself to the sea floor. Sometimes we even find trace fossils, not the creatures themselves, but the evidence of their activity, burrows, tracks, feces, feeding marks. These are especially valuable in the Precambrian and early Cambrian, when soft bodies rarely survived but movements did. The twist of a spiral in the mud, the crawl of a belly across silt, the puncture of a feeding tube into microbial mat. It's in these traces that we glimpse the behaviour of the first animals, and alongside behaviour we study form. This is where morphology and developmental biology join forces. Scientists analyse body plans, how limbs branch, how heads form, how symmetry is organised. They compare modern embryos with fossil shapes. They map genes like Hox genes, which control body segmentation and identity across species. These genes are astonishingly ancient. The same Hox genes that direct limb development in humans are found in flies, worms, jellyfish. They are not just blueprints, they are time travellers, carriers of biological memory. And their distribution across species allows researchers to build phylogenetic trees, diagrams that show evolutionary relationships. These trees are not perfect, they shift with new data, but they allow us to place strange Cambrian creatures within a broader narrative. This one was likely an early arthropod. That one, maybe a basal chordate. That one, possibly a failed lineage. The point is not always to classify, but to understand potential. What paths life tried, what succeeded, what didn't. But genes aren't the only clue. To understand ancient animals, we must also understand the world they lived in. This is where geochemistry becomes a kind of planetary stethoscope. By analysing isotopes in rock, versions of elements with different numbers of neutrons, scientists can reconstruct past environments. Carbon isotopes tell us about photosynthesis, productivity, and global carbon cycles. Oxygen isotopes can be used to estimate past temperatures based on how they fractionate in water. Sulfur isotopes hint at microbial activity and the presence of anoxic or oxygen-free zones. In Cambrian rocks, geochemists have discovered strange pulses, brief periods when carbon isotopes shifted sharply, or when ocean chemistry turned hostile. These may reflect mass extinction pulses, algal blooms, volcanic events, or other sudden changes in the biosphere. By layering this data, fossils, isotopes, sediments, trace elements, we build a composite portrait of early Earth, a multi-dimensional view that blends biology, chemistry, geology, and physics, and the portrait is nuanced. The early Cambrian was not uniformly friendly. Oxygen levels were likely highly variable. Some areas were oxygen-rich, others hypoxic. Animals had to adapt to these fluctuations by evolving tolerance, burrowing into stable zones, or retreating into microbial shelters. Some researchers now believe that oxygen gradients may have been key drivers of body plan innovation. Where oxygen was scarce, life remained simple. Where it spiked, complexity surged. This ties into a broader question. Was the Cambrian explosion triggered by environmental change? Many believe so. A combination of rising oxygen levels, increased nutrient availability from erosion, tectonics or glaciation, and ecological feedback loops, like predation and competition, may have crossed a threshold. Once that threshold was passed, life expanded into new spaces, both literally and figuratively. But others argue that the genetic toolkit for complexity was already in place long before the Cambrian. Genes for muscles, nerves, adhesion, patterning, they all existed. It was only when the right ecological pressures emerged that these latent capabilities were expressed. This is where climate modelling and ecosystem simulation come in. Scientists use computer models to recreate ancient oceans, simulating currents, temperature gradients, oxygen flows, and species interactions. These models test scenarios. What if ocean mixing increased? What if sulfide levels dropped? What if grazing pressure triggered plankton turnover? By simulating these worlds, we see which conditions could have supported early animal life, which ones led to flourishing, which to extinction. It's not just theoretical. These models are grounded in real data, fossil counts, geochemical measurements, sediment layers, climate proxies. They're like rehearsal spaces for Earth history, test kitchens for evolutionary recipes, and they offer insights we couldn't get from fossils alone. For example, they help explain how small changes in continental position, the drift of tectonic plates, could open or close ocean gateways, altering global circulation patterns, or how glacial runoff could change nutrient flows, or how early animals might have triggered feedback loops by altering sediment stability and bioturbation rates. These are big systems, but they often turn on small hinges. A worm burrowing into oxygen-poor mud, a sponge filtering enough water to clarify the sea, a predator pushing prey to evolve armour. Biology becomes geology, ecology becomes climate, and all of it in the end becomes history, Even biomarkers, chemical traces of life left in ancient rock, add to the picture. These include molecules like steranes, hopenes, and porphyrins, which are unique to certain kinds of cells. Their presence in Precambrian sediments tells us when eukaryotes, algae, and perhaps even early animals began to spread. In some cases, we even find fossil embryos, preserved in phosphatic nodules showing cell division, blastulation, gastrulation. These allow scientists to trace developmental pathways through deep time. Imagine that. A fossil, 500 million years old, showing the shape of an embryo as it begins to form. It's a kind of time-lapse memory, paused in stone. And this brings us to another frontier, molecular clocks. These are methods that estimate when lineages diverge based on the rate of genetic mutation. By calibrating these rates with known fossil dates, scientists can work backward to estimate when key animal groups first emerged. Some molecular clock studies suggest that animal lineages diverged tens of millions of years before the Cambrian, in the Ediacaran, or even earlier. If true, this means that the genetic groundwork was laid long before animals left abundant fossils. They were there, but hidden, soft, sparse, waiting for their moment. Of course, molecular clocks are tricky. Mutation rates aren't constant. They vary by lineage, by gene, by time period. Calibration is difficult. But when used carefully, alongside fossil and geochemical data, they add yet another layer of inference. And inference is ultimately what deep science is about. We will never see the Cambrian with our own eyes. We will never touch an Anomalocaris or swim with Pikaia. But by layering evidence, bones, molecules, isotopes, behaviour, we create images that are truer than imagination. Reconstructions not of fantasy, but of informed wonder. In the next and final chunk of this part, we'll go even deeper, exploring how ancient proteins are reconstructed, how scientists use modern analogues to study ancient life, and how astrobiology, yes, life beyond Earth, uses the story of the first animals to search for life elsewhere. When we study the rise of the first animals, we aren't only looking backward, we're building a bridge between deep past and deep future. Because many of the tools used to study ancient Earth are the same ones we now use to peer outward into space, or downward into the building blocks of life itself. And as strange as it sounds, the origins of animals have become part of astrobiology, the science of life beyond Earth. But let's take that connection one step at a time, because before we can talk about distant worlds, we need to talk about something very close: proteins. In the last few decades, scientists have begun attempting the near impossible, reconstructing ancient proteins, not just imagining them, actually resynthesizing them in the lab. Here's how it works. By analysing modern genomes across a wide diversity of life, researchers use algorithms to infer ancestral sequences, the likely combinations of amino acids that would have formed key enzymes hundreds of millions, even billions of years ago. Once they have a likely candidate, they synthesize the gene, insert it into bacteria, and let it express the ancient protein. The result? A molecule that hasn't existed since before complex animals evolved, now active in a petri dish. Why do this? Because proteins are the engines of life. They perform nearly every cellular function, metabolizing sugars, building membranes, copying DNA, responding to heat, light, and danger. And by resurrecting ancient versions of them, we can understand how early life worked, how cells adapted to low oxygen, how enzymes functioned in high-sulfur environments, how evolution sculpted molecular efficiency over geological time. Some of these resurrected proteins even prefer ancient conditions, functioning better in hotter, more acidic environments that mirror the early oceans. Others reveal unexpected flexibility, showing that early life may have had more biochemical diversity than we realized. This flexibility may have allowed life to survive the many upheavals that preceded the Cambrian explosion: glaciations, anoxic oceans, volcanic winters. Proteins, then, are not just molecular tools, they are survivors, Each one tells a story written in shape and function, and these molecular stories link directly to broader evolutionary questions. Consider oxygen-sensing proteins, like hemoglobin precursors. How did early animals respond to fluctuating oxygen levels? Could they turn genes on or off? How do their cells know when to adapt? Or take photoreceptive proteins, the ancestors of those that now help us see? What were their original roles? Were they light sensors in plankton, heat detectors? How did vision emerge from molecules? By tracing these threads, we begin to understand how complex traits like vision, movement, and neural coordination may have emerged not suddenly, but from the repurposing of ancient tools. And this principle of old parts used in new ways has become one of the defining ideas in evolutionary developmental biology, or Evo-Devo. Evo-Devo studies how genes control development and how small tweaks in timing or expression can lead to large differences in form. A limb becomes a fin becomes a wing, a shell becomes a skull. And often, the same genes are involved, just deployed differently. This has massive implications for how we view the Cambrian explosion. Rather than a sudden invention of new genes, it may have been a rewiring of existing ones, a shift in expression patterns, a release of constraints. The genetic toolkit for building animals was already in place. The Cambrian simply turned the key. To test these ideas, scientists often turn to modern analogues, creatures that live today but resemble ancient forms. Sponges, comb jellies, placozoans. Their genomes, physiology, and behaviour offer clues to ancestral states. Sponges, for instance, lack nerves and muscles, but their cells respond to signals and contract in coordinated ways. This suggests that the foundations of nervous systems existed before neurons themselves. Chemical gradients, mechanosensitivity, calcium signalling, all present, all co-opted. Or consider ctenophores, the comb jellies. Once thought to be simple, recent studies suggest they may have evolved nervous systems independently. Their neurons use different molecular machinery. If true, this would mean brains evolve more than once. A stunning idea, and one that challenges how we define complexity. But it's not just what lives today that helps us understand the past. It's also what no longer lives, or rather, what no longer leaves fossils. That's where molecular dark matter comes in. This is the vast landscape of genes, regulatory elements, and non-coding sequences that don't show up in fossils. They exist in living genomes, but their functions are only dimly understood. Some may be remnants of ancient viral infections, others may be the scaffolds for developmental control, some lie dormant, others respond to stress. Together, they form a kind of genetic memory, one not visible in stone, but essential to life's story. And when we consider this hidden genome, we begin to see how much of early animal evolution may remain invisible to fossils. A gene may change how a creature looks, but it may also change how it reacts, how it learns, how it ages. This deep layer of biology, below the bone behind the phenotype, adds richness to the story of animal origins. And now it's beginning to inspire other sciences. Because if life could emerge from Earth's early chaos, under pressure, in darkness, with few resources, then maybe it can emerge elsewhere too. This is where astrobiology enters. Astrobiologists study extreme environments, hydrothermal vents, acidic lakes, subglacial oceans, places where microbes still thrive, and they ask, if life began here, could it begin elsewhere? They build models of prebiotic chemistry, how organic molecules assemble, how membranes form spontaneously, how catalysts emerge. They use simulations of ancient Earth to refine the search for biosignatures on Mars, Europa, Enceladus, exoplanets. And in those simulations, the story of the first animals matters, because their rise marks a threshold, when life began to shape its environment at scale, when ecosystems developed feedback loops, when behaviours emerged that could be detected from afar. Some researchers now ask, could a planet's biota ever leave an atmospheric fingerprint? On Earth, Animals changed oxygen levels, methane cycling, cloud formation. Could similar changes be seen on other worlds? In this way, the first animals become part of a much larger search, not just for fossils, but for patterns, for signals, for intelligence, however it arises. And that brings us back to Earth, with a new sense of perspective. Because we often treat the story of animals as a closed chapter, a solved puzzle, but it isn't. The Cambrian is still being excavated, the Ediacaran is still debated, genetic data still reveals surprises, and even the definition of an animal continues to evolve. Are animals defined by movement, by multicellularity, by embryonic development? What about colonial protists that blur the line between organism and colony? What about viruses that co-opt host behaviour? Each new discovery reminds us that life resists neat categories. It flows, it adapts, it leaps across boundaries, and so must we, if we wish to understand it. This is why deep science matters, not just as data, but as invitation. An invitation to humility, to awe, to the recognition that the world is older, stranger, and more interconnected than we can easily grasp. The rise of animals wasn't a crescendo. It was a conversation between chemistry and contingency, between silence and complexity, between the deep earth and the restless sea, and that conversation continues in rocks, in genes, in experiments, and perhaps most beautifully in questions. Because even now, after centuries of study, we're still asking, how did animals begin? Why then? Why that shape? Why that path? And with every answer we find, new questions bloom, like coral, like cells, like life. When we speak of explosions, biological, geological, chemical, we tend to focus on the detonation, the instant, the spectacle. But in nature, the most profound changes often come not in bangs, but in echoes, long, slow, almost imperceptible ripples that continue long after the fire has dimmed. And so it was with the Cambrian. The explosion itself was brief, by geological standards, 20, 30 million years at most. But its aftershocks have never stopped, because once animals arose, they didn't simply flourish. They transformed the world around them. They altered sediment, chemistry, ecosystems, and each other. They invented predation, symbiosis, competition, locomotion, reproduction in new and strange forms. And after the initial surge of forms, the Earth entered a kind of evolutionary exhale, a long stabilization, a settling. The Cambrian gave way to the Ordovician, and with it came structure. Reefs expanded, growing not just from microbial mats, but from the bodies of animals themselves. Tabulate corals, bryozoans, stromatoporoids, life learning to build in layers, to reach upward toward the enlightened current. Animals moved into ecological roles. Filter feeders, grazers, scavengers. Trilobites developed complex eyes and behaviours. Nautiloids evolved chambered shells and swam with jet propulsion. Graptolites drifted in the water column, recording their presence like calligraphy and stone. The oceans became stratified, not just physically but biologically. Some animals clung to the seafloor, others swam freely. Some burrowed into sediment, reworking the very structure of the seabed. This process, called bioturbation, sounds simple, but it was revolutionary. Before animals, sediments were layered and undisturbed, finely laminated, almost static. But with worms and arthropods digging and shifting, sediments became mixed, aerated, disrupted. This changed how oxygen and nutrients moved through the ocean floor. It changed microbial communities. It changed the burial of carbon. Animals, in essence, turned the seafloor upside down, and this in turn fed back into global cycles. Carbon began to be buried more deeply. Oxygen levels rose. The Earth cooled slightly. Life made the planet more livable for itself. But recovery wasn't a straight line. The Ordovician ended, as we've seen, in one of the planet's first major mass extinctions, likely driven by a brief but intense glaciation. Sea levels dropped, habitats shrank. Many marine invertebrates, especially those with narrow ecological tolerances, disappeared. And yet, even in this loss, new opportunities emerged. After the extinction, survivors diversified again. This pattern, collapse followed by radiation, would repeat across Earth's history. Extinctions are not endings. They are editorials. They prune the tree of life, often ruthlessly. But they also make room for new growth. In the Silurian, corals recovered. Fish diversified, both jawless and jawed. Vascular plants began to appear on land, humble and low to the ground, but laying the groundwork for future forests. By the Devonian, life was on the move again. Fish became more elaborate. Placoderms with bony armour, acanthodians with spines, early sharks. Lobe-finned fish evolved lungs and limbs, adaptations that would eventually carry them onto land. Insects took to the air. Fungi formed alliances with plants. The first forests grew, roots reaching down, leaves up. And still, animals kept adapting. Through these long periods of change and stabilization, the ecology of the planet matured. Niches became more refined, predator-prey dynamics intensified, shells grew thicker, jaws stronger, eyes keener. What began as simple multicellular motion became an arms race of form and function. But the Cambrian legacy wasn't just biological, it was geological. The remains of Cambrian and Post-Cambrian animals accumulated into vast limestone deposits, shaping entire mountain ranges. Their shells formed the carbonate platforms of ancient seas. Their activity changed the deposition of sediments, the burial of organic matter, the oxygenation of the ocean. In short, animals began to write their story into the planet itself. This was no longer a microbial world, it was an animal Earth. And yet, for all their influence, many of the early Cambrian lineages didn't last. Trilobites, once rulers of the seafloor, declined over hundreds of millions of years, finally vanishing in the Great Permian extinction. Morellomorphs, radiodonts. The strange forms of the Burgess Shale. Most were pruned away. Survivors gave rise to new branches. Arthropods split into crustaceans, insects, arachnids, vertebrates into fish, amphibians, reptiles, birds, mammals, mollusks into snails, clams, cephalopods. And along the way, animal body plans became canvases for new invention. Some grew wings, others lost limbs, some developed social systems, echolocation, venom, camouflage, electric senses, and one eventually grew a brain so reflective it could ponder the Cambrian itself. But here's the quiet beauty. All of this began in water, in the shallow marine shelves of a long-vanished sea. The soft stirrings of the Cambrian led, in slow increments, to everything we now see in zoos, oceans, rainforests and sidewalks, and not just in body, in behaviour. The rise of nervous systems, of sensory organs, laid the foundation for interaction, for learning, for memory, for cooperation, eventually for language, for culture, for art. The first animals may not have known they were alive, but over time, life began to notice itself, to reflect, to name. But not all legacies are gentle. As animals reshaped ecosystems, they sometimes destabilized them too. Overgrazing of microbial mats may have collapsed certain early niches. Burrowing altered sediment dynamics. Predator-prey cycles led to booms and crashes, and much later, one animal, Homo sapiens, would harness the power of tools, fire, agriculture, fossil fuels. We became not just participants in ecosystems, but shapers, disruptors, guardians sometimes, but also threats. The long-term consequences of animal life now include climate change, habitat loss, mass extinction, pressures unlike any since the asteroid that ended the dinosaurs. And yet the resilience of life continues. Many of the adaptations born in the Cambrian still serve today. Muscles, nerves, circulatory systems, segmentation, bilateral symmetry. These are not historical accidents. They're durable frameworks, flexible blueprints. They've been tweaked, repurposed, elaborated upon, but their roots remain deep. Even your breathing, as you read or drift, follows rhythms that first emerged in oceans 500 million years ago. Even your eyes, moving gently across these words, use proteins with ancestry in single-celled photoreceptors that once floated, unseeing, near the surface of a Cambrian tide. We carry these stories not just in memory, but in biology. So when we speak of long-term consequences, we don't mean just planetary change, we mean us. We are, in a very real way, the latest chapter in the slow recovery, the continuation of those first animals, the thinking tip of a deep, winding route that stretches back through time, and like the trilobite, we too will leave traces in rock, in bone, in carbon, in story, because Earth forgets nothing. Its memory is slow but precise. Every ripple leaves a mark, every breath adjusts the balance, every extinction opens a door, and through it all, life continues, changing, collapsing, reinventing, but always moving forward, even when it moves in circles, even when it forgets and remembers itself all over again. We began with a question. Who were the first animals? We followed it into rock, into molecule, into oceans long gone. We watched sponges rise, eyes blink open, predators take their first bite. We crossed epochs like stepping stones, Cambrian, Ordovician, Devonian, each one a different rhythm in Earth's long breath. But now, as we near the end of this story, it's time to ask a different kind of question. Why does it matter? Why spend an hour thinking about trilobites and worm burrows and ancient oceans? Why sift through ashes of time for creatures that vanished before the first tree grew? The answer, I think, is quiet, but it's real. Because the story of the first animals is not just a story about them, it's a story about us. Not in the egocentric way. This is not a tale that ends with humans as the triumphant crown of evolution. The story doesn't build to us. We are not its climax. We're just here. A recent whisper in the long, long sentence of life. But that doesn't make our part small. It just makes it shared. Because when you look at a fly, or a sea star, or a jellyfish pulsing under moonlight, you're not looking at something separate. You're looking at family. At an echo of the same chemical story, the same coiled code, the same ancient accident of becoming. We are the latest in a long line of animals, and that lineage holds wisdom. It tells us what life can survive, what it cannot. It shows us that innovation comes after collapse, that ecosystems can rebuild, slowly, painfully, but only when the damage halts. That resilience has a rhythm, but even rhythms can be broken. And that's the sobering part of this story. Because Earth has seen 5 mass extinctions. We are living in what some now call the 6th. Species vanish daily. Coral reefs bleach. Insects fall silent. Ice melts. Patterns shift. The difference this time is speed. The difference is us. We are changing the planet faster than at any point since the asteroid. And unlike the asteroid, we have a choice. And that's where the ancient story becomes modern. Because animals arose not just as life forms, but as participants in Earth's balance. Their rise changed the planet, yes, but always through feedback, through give and take. Sponges cleared the seas but didn't drain them. Worms stirred the mud but didn't poison it. Now, for the first time, one animal species holds the tools to change the biosphere at scale, intentionally or not, and we're still learning how to handle that weight. But perhaps the deep past has something to teach us. It teaches us patience. The Cambrian took millions of years to unfold. It teaches us humility. Most animal lineages didn't make it. It teaches us perspective. Extinction is not rare. What's rare is continuity. And it teaches us that life is not just persistent, it's collaborative. Every ecosystem is a network. Every species, a node. Even extinction reshapes what's left behind. That's how evolution works. But it also teaches us that the biosphere has limits. You can't bleach all the reefs and expect fish to find shelter. You can't warm the oceans endlessly and expect the plankton to bloom. And you can't erase whole niches without consequences. Because if the Cambrian taught us anything, it's that complexity is earned. It's layered. It's delicate. A single pressure. Too much sulfur, too little oxygen, too many volcanoes can unmake it. And if that's true, then so is this. What took 500 million years to build can be unravelled in a geological heartbeat. But this isn't a story of despair. It's a story of possibility. Because when you understand how animals first emerged, you understand how unlikely it was, how beautiful, how fragile, and how miraculous it is that life continues at all. And in that knowledge, something changes. You begin to look differently at the world. That ant trail in the soil, that spiral of a snail shell, that flicker of a bat's wing against twilight. You realise these aren't just casual creatures, they're survivors, descendants of those same Cambrian pioneers. Their DNA is filled with the same innovations, the same constraints, the same story told a million different ways, and we're part of it. The same molecules that drove the first muscle contractions still drive your heartbeat. The same nerve impulses that let a Cambrian worm detect movement in the water now fire when you feel fear, or joy, or grief. Evolution didn't end with us. It continued into us. And now, we are the storytellers. We are the ones who dig, who ask, who remember. We write books. We make films. We whisper facts into microphones and upload them to digital clouds. We teach children about trilobites and ancient seas. We gather around museum cases. We build computer models of vanished worlds. And in doing so, we give the Cambrian a second life, not in flesh, but in mind. We extend the legacy of the first animals through reflection, through attention, through care. And perhaps that's our role now, to be witnesses, to be caretakers, to be the nervous system of the biosphere, aware of itself. Because life is no longer blind. It knows what it is. It knows what it's risking. And it still has time to change. We can't undo the past, but we can respond to it. With wonder, with action, with reverence. And with that old human instinct that's carried us this far. Curiosity. So if you ever feel small or lost, or unsure of your place in the vast story of things, remember this. You are the distant echo of an ancient tide. You're stardust and salt water, reorganized into thought. You're a question asked by the universe, slowly learning to answer itself. And every breath you take is a continuation of lungs first born in fish, of genes first sorted in slime, of motion first sparked in silence. You're not apart from this world. You're of it. And the first animals, soft-bodied, strange, nearly forgotten, are not gone. They live in you. And so, dear traveller, we've come to the quiet end of our journey. From ancient oceans to the softest stirrings of sensation. From burrows in Precambrian mud to the rise of eyes and teeth and possibility. From fossils hidden in mountain tops to molecules pulsing in every cell of your body. The story of the first animals is vast, strange, humbling, and somehow still unfolding. If you've made it this far, I want to thank you. Not just for listening, but for wondering. For allowing your thoughts to stretch across 500 million years. For giving space in your night to the silent drama of deep time. For remembering lives that never knew they would be remembered. If this helped you find stillness, if it sparked curiosity, if it kept you company as sleep tiptoed in, I hope you'll consider leaving a like, maybe subscribing to Just About Earth, or even sharing this with someone who might enjoy drifting through the stars and stones with us. And if you have thoughts, questions, or dreams sparked by tonight's tale, I'd love to hear them. Leave a comment, start a conversation. After all, the story of life is not something we inherit passively. It's something we continue together. In the next chapter, we might explore another ancient mystery, maybe the tale of Earth's first forests, or the origin of colour, or the day the sky turned red. But for now, let this be enough. Let this quiet linger. The world outside may turn fast, but here, in this moment, time flows slow. And beneath it all, the story of life goes on. Sleep well, dream wide, and thank you for spending a little of your evening with Just About Earth. Good night.